All right, welcome back. So we're moving on to our second searching algorithm, and this one can be a significant improvement on linear search that we saw in the last video. It's called binary search, so it can be much, much faster. We'll get into the specifics with big O later on, but it can be faster. Rather than eliminating one element at a time, like we did in linear search where we checked one element, is this it? Nope. Is the next one it? Nope. Is the next one it? Over and over and over. In binary search, we can eliminate half of the remaining elements at any given point. However, there's a really big caveat here. Binary search only works on sorted arrays. So the data has to be sorted from, if it's numbers, lowest to highest, or highest to lowest, or strings, alphabetical, there has to be an order to it. So imagine we have our same states array. You don't have to imagine because it's right here. And this is sorted alphabetically. So you can see Alabama down to Wyoming. And let's say that we're doing the same example where we ask a user to enter a state and for their address or something, and we're going to verify that it exists in this array. Now, first of all, this is a very short array in the grand scheme of things, so linear search isn't really going to be it's not going to take much time, and the milliseconds, probably less than a millisecond. The tiniest fraction of a second that we're saving with binary search isn't really worth it. But since it's already sorted, it's a good example. Let's say that someone enters Oregon as their state. So in quotes, and we want to check if that's in here. Well, since it's sorted alphabetically, the way that binary search works is that we pick a halfway point in this array. So somewhere, and I'm not going to count exactly, I think there's 59. I'm not going to count the exact halfway point, but let's just guess roughly. Let's say that we pick states of, I think 29, it's 29.5, right? So we'll round down. So we pick our first spot, we pick the middle because we know it's sorted, in this case alphabetically. So the middle should be the middle sorted element. And then all we do is we check. So we find Missouri, there you are, and we check, is Oregon greater than Missouri or less than? In our case, alphabetically, is it after M, Missouri? Is it after that in the alphabet, or is it before? And it's after. So now we only care about this part of the array. We've just eliminated all of this. We don't care about the beginning. And we check halfway through the next little bit. And I'm just going to eyeball it rather than doing the math. But let's say halfway through is around 44. So let's say check states 44. That gives us Pennsylvania. So now this is the middle of this array here. And we go to Pennsylvania and we check, is Oregon before or after Pennsylvania? And it's before. So now we care about this list. From Missouri to Pennsylvania, we know that it's somewhere in here. We eliminated all of this here. So now we're going from Missouri to Pennsylvania and we pick the halfway point again. And I think this is 16 or so. So let's go to the eighth one, 3, 4, 5, 6, 7, 8. So we go to New York and we check, is Oregon greater or less than New York? And it's greater, so it's between New York and Pennsylvania. So we pick somewhere in the middle between New York and Pennsylvania. Let's say that it's Ohio. And we know that it's greater than Ohio, so it's somewhere between Ohio and Pennsylvania. We pick the middle, and now it's Oregon. And I know that seemed like a lot of work, but remember that was only, 5 or 6 guesses compared to if we started at the beginning with a linear search. We check this. Is this Oregon? Nope. Is this Oregon? Nope. Over and over and over. So it saves a lot of time if your data is sorted. So let's get down to the details of the implementation. So the idea is dividing and conquering. So we split up the array into 2 pieces. We pick a pivot point in the middle usually, and we check the left side and the right side and see where, based off of what we're looking for, where it will be in which half. So let's search for 15 in this list. Remember, it has to be sorted. This doesn't work at all if it's not sorted. So if it's sorted here, we're going to start by picking, we're going to call them left and right. So we're going to change the window of where we're searching because remember, we can throw out half of the array roughly every time. So we're going to start with left at 1 and right at the end, 19. And then we're going to pick somewhere in the middle. And I think this is an odd number, so you can round down or round up, just be consistent as far as where you pick. So I think we're going to pick 11 here. I know we're picking 11. And we check, is 15 greater than 11 or less than 11? And it's greater than. So now we eliminate all of that to the left, and we make the new left 12. And the new right is the same, it's 19. Now we check somewhere in the middle. So we're going to check 17 as our middle point. And we check, is 15 greater than or less than 17? Is it on the right side or the left side? and it's on the left side. So we can eliminate 17, 18, 19, and now we have a left at 12, a right at 16, and then the middle is 15, which is our only choice, and we check, is 15 equal to 15? Is it greater than or less than? And it's equal, so we found it. So that only took 3 checks, 3 guesses. We checked at the middle first, 11, and we knew it was greater, so we did a second check. We picked 17, that was too big, and then we picked 15, and that was correct. Compared to starting at the beginning, 1, 2, 3, 4, 5, 6, 7, 8, 9 guesses using linear search. So if we have a sorted array, numbers or strings or whatever it is, as long as we can compare easily to check if something is greater than or less than in some respect, if we can do that, then we can implement binary search, which is much faster.